Hello, Physics 1. Welcome to part 1 of Monday's lecture, week 17. Hooray! And we're going to be continuing on in chapter 11, starting with an example where we look at doing some cross products. So, say we've got a shape. It's a grid. All right, so let's draw. All right, so we've got, these are 4 meters on the bottom, 3 meters here, and 5 meters. And let's give it some labels. So A, B, C, D, E, F, G, H. And we've got a momentum vector where P is equal to 10 kilogram meters per second. Okay, so we are going to calculate the angular momentum relative to B. So and we've got momentum, and we've got everything we need to find a position vector. And this is the point that it's all going to be relative to. All right. So we can do this using a vector cross product. So position with respect to B from here is equal to minus 4, because you have to go back 4 this way, up 3 and 0, it's a two-dimensional picture. And momentum is equal to 10, 0, 0 kilogram meters per second. All right, so set up, we know that angular momentum with respect to B is equal to RB cross P. Set up IJK. IJK. IJ minus 4, 3, 0, minus 4, 3, 10, 0, 0, 10, 0. All right, do our cross product. So 3 times 0 minus 0. 0 times 10 minus 4 times 0. 0. Again, unsurprising. We've got components that are both in x and y. We would expect an answer in z, so we are getting what we would expect. And then we have 10 times 3 minus 4 times 4. Sorry. Minus 4 times 0 minus 10 times 3. So minus 10 times 3, which is 0, 0, minus 30 kilogram meters squared per second. Okay, so we could find angular momentum with the cross product. All you need are the two vectors, and then you do the cross product operation on them to get a three-dimensional answer. It will include direction, no right-hand rule necessary. We could also look at the direction and magnitude of RB using P sine theta. So with a problem like this, you might be asked to do both, or you could simply be asked to solve for the angular momentum. You choose what works for you. Okay, so we would have so that's our setup. Now, in order to do this type of cross product, we're going to want to move this tail to tail. So essentially you're moving this vector up. So then you have RB, P. All right, so R cross P line up with R. There it is. Fold towards P. Negative, confirming our previous results. So we have negative Z as calculated. We need the magnitude RB. 3 squared plus 4 squared is equal to 5m. P is equal, the magnitude of P is equal to 10 kilogram meters per second. LB is equal to minus RB times P sine theta. We don't have a theta yet, so let's look at that. So we've got the 3. So we know this is 3, we know this is 4, going back to our original drawing. There you go. This is 5, we'd have alpha sine theta is equal to 3/5. Using SOHCAHTOA, opposite over hypotenuse. And so LB is equal to 5 meters times 10 kilogram meters per second times 3/5 is equal to 30 kilogram meters squared over seconds. Using the right-hand rule, we know it's in minus Z. Then we can put this all together and we get 0, 0, minus 30 kilogram meters squared per second. So 2 different ways of solving the same problem. Either way, whether you're using magnitudes, the magnitudes of the vector and the sine of the angle theta between them, and then using the right-hand rule to find direction, or you're taking a cross product, you will get the same result. Do what's easiest. Always do what's easiest. No brownies for doing things the hard way unnecessarily, unless you're asked to use multiple methods. All right. So moving on to rotational angular momentum. So we know how to calculate translational angular momentum of a point particle. Now let's look at an object spinning on its own axis. So, if you recall from chapter 9, K is equal to the sum of the translational kinetic energy plus the relative kinetic energy. And we're going to see a similar approach to describing angular momentum, that you're going to have a translational component and a relative component. So, let's start by once again considering a bike wheel. It's spinning. Whew. Noisy. All right, so bike wheel with mass m spinning on axis. With a stationary axle. All right, so as we've talked about with bike wheels before, most of the mass is in the wheel. So we're going to divide this into 20 even pieces. So one piece has a mass of m/20. And each piece has a speed, so the speed of one piece is v is equal to omega r. Okay, so using this, the magnitude, the angular momentum, center of mass of one piece is r m/20 v sine of 90 degrees. This is equal to r m/20 omega r, which is equal to m/20 r squared omega. And if we use right-hand rule for direction, so in the original drawing, we can see that it's spinning in this direction, curve our right hands, negative z. So we know that our angular momentum is in minus z. And to get total L, we need to add the pieces up. So the angular momentum of the center of mass is equal to 20 m/20 r squared omega is equal to m r squared omega. Every piece is the same distance from the center of mass with a bike wheel. So, and also if you recall, the moment of inertia for a loop, for a bike wheel, ring, hoop, whatever you want to call it, I is equal to m r squared. I is equal to m r squared. So therefore, the magnitude of the center, the angular momentum of the sun towards the center of mass is equal to the moment of inertia times omega. And also what you can see is the number of pieces didn't matter. They were going to cancel out no matter what. I could have said, let's divide it into 2 million pieces of equal mass, and we would have canceled out 2 million. All right, so we know about angular velocity. Now notice, I've been calling it angular velocity, not angular speed. That is because angular velocity is also vector. And it's denoted by an omega with a little vector over top. And the magnitude, we've got radians per second. And you determine direction using the right-hand rule. So omega in this direction, you have omega out of the page. spinning in this direction, you've got omega into the page. All right, so an angular momentum of a system relative to the center of mass is rotational angular momentum, just like we saw with kinetic energy. So for a bike wheel, rotational angular momentum is equal to I omega, where I is equal to mr squared. Okay, so let's do an example. We're going to use a fat tire bike wheel. Ugh, that is a bike I do not have, and I so want one. Surly ice cream truck fat bike. All right, so a fat tire bike wheel has a mass 1.086 kilograms and radius 36.5 centimeters. And it's rotating in XZ. And you can, if you view this from Y, it's clockwise when viewed from plus Y. So it makes 1 revolution in 0.68 seconds. So what is the rotational angular momentum? Okay, so it's going clockwise. If we turn our hand clockwise, we see it's going in. We know it's going to be in Y, so therefore the direction of angular velocity is minus Y. So the moment of inertia is equal to mr squared. This is equal to 1.086 kilograms times 0.365 quantity squared. The moment of inertia is equal to 0.145 kilogram meters squared. Omega is equal to 2 pi over 0.68, which is equal to 9.241 over seconds. The magnitude of rotational angular momentum is equal to 0.145 kilogram meters squared times 9.241 over seconds, plugging this in to our expression. And so we get this is equal to 1.334 meters squared over second. And we've already determined the direction of rotational angular momentum, 0 minus 1.33, that's a 3, for 0 kilogram meters squared per second. Okay, so there you go. There's an example with rotational angular momentum. So we can write it out explicitly. Rotational angular momentum and this is for a rigid object where all components rotate around the center of mass with the same angular velocity. So you can't have like a floppy object. That doesn't work. And then you use the moment of inertia that corresponds to the shape. And we can express rotational kinetic energy in terms of rotational angular momentum. So if rotational angular momentum is equal to I times omega, so I've left the vector signs off. We're dealing with magnitudes right now because kinetic energy is a scalar and not a vector. Rotational kinetic energy is equal to 1/2 I omega squared is equal to 1/2 I omega quantity squared over I. So I've put in a clever one. You can always multiply something by 1. It's always valid. And this is simply L rotational angular momentum squared over 2 times the moment of inertia. There you go. So you can get one from the other. All right, we'll stop lecture or part 1 here, and I'll see you next time for part 2.